Okay, good morning. Today I will finalize this mathematical induction and then this chapter is finished. So to warm up, let me start with an exercise. We had something we had similar to that before, but in trigonometry. Okay, so let me ask you to do this. For any natural number n, show that, so we have this. Cosine x multiplied by cosine 2x multiplied by cosine to the power of 2 times x. Let me put them in pairs of brackets, of course it is not necessary. And then you continue multiplied by cosine 2 to the power of n x. You're supposed to show that this product is equal to sine to the 2 to the power of n plus 1 x divided by 2 to the power of n plus 1 multiplied by sine x. Okay. So here, first of all, you see that there are two variables involved. One of them is n, the other one is x. And of course, x can be any real number. And you know that you can use mathematical induction only on natural numbers, yes? So it means that if I want to solve this problem using mathematical induction, I have to use my induction on the variable n, not variable x. On variable x, it is meaningless. Okay, and then if I want to show that, I take the whole statement, this equality, to be statement Pn. Yes, so I call it Pn. And then I have to check P of 1. Okay, so it means that I need to read the statement for n equals to 1. But how should I read the statement? This tells you that you take cosine 2, yes, 1x times 2 to the power x up to 2 to the power of nx. Okay, so P1, on the right hand side it is clear. Wherever I see n, I replace it by 1. Yes, so the right hand side becomes sine 2 to the power of 2 x divided by 2 to the power of 2 sine x. That is what is on the right hand side when I replace n with 1. But can you tell me what happens for the left hand side? So what should I write for the left hand side if n is equal to 1? Yes?
Cosine x times cosine 2x.
Yeah, so that's, I hope that this is clear from the previous lesson. So if I put 1 here, this generates cosine 2x. But cosine 2x is not just simply the first term, it is the second term. So if you want to write P1 in a correct way, the left-hand side will read cosine x times cosine 2x. If you don't interpret it correctly, then you might get that P1 is not right. But it is. So let us check. So I have to check this is the correct statement. Okay, so usually P of 1 is very trivial to do. But it is a little bit complicated here, so you have to know how to do it. So even if I want to check the P of 1, the truth of P of 1, it is not that trivial, yes? So I have to do some trigonometry to be able to show that the left-hand side is equal to the right-hand side. So this I need to check. To see if this is true or false. I think it is better to start from the right-hand side here. So I will start from the right-hand side of this. First of all, 2 to the power of 2 has a better name, so let me write it 4. The same is true for the denominator, 4 sine x. So this is the right-hand side. But then you know that we have a double angle formula, yes? If I have sine of 2 any angle theta, this becomes 2 sine of the angle divided by 2 times cosine of the angle divided by 2. So that we learned in chapter 1 under the title of the sine of double angles. Okay, so here we can use that formula for the numerator. Because this is 4x, I can divide it to 2, so this becomes what? According to that formula, this becomes 2 sine of my angle divided by 2, which becomes 2x, multiplied by cosine of my angle divided by 2, the same 2x. And the denominator, I will have 4 sine x. But, again, I can use the same formula for this combination sine 2x, and then it gives me another 2. That 2 will be multiplied here by that 2. It becomes 4. And then sine of the half of the angle, which is x, multiplied by cosine of half of the angle, which is x again, and then multiplied by cosine of 2x. And then again divided by 4 sine x. So, yes, so I just use this formula once more for this combination. In the formula I have a 2, which will multiply by this 2 will give me 4. And then you immediately realize this 4 and that 4 are cancelled. This sine x and that sine x are cancelled. What is left for me is cosine x, cosine 2x. And you see this is exactly the left-hand side of this one. So this is probably the first example that you've seen, which you have to do some work even for P of 1. Usually P of 1 is very trivial. But this is you have to do it for P of 1. So at least this statement is true for P of 1. And be careful. If you have just written cosine x on the left, then you might think that this is not a correct relation. So you have to interpret it correctly. So if I want to give you a rule of thumb for these products or sums including these dots, you put n equals to 1 in the very last term. If you get the first term, you keep the first term. If you get the second term, you keep the first and second. If you get the third term, you keep the first, the second, and the third. So that is the rule of thumb if you want to do it quick. Okay, so now we assume that P of k is true. So I'm assuming that k is a natural number, an arbitrary natural number, and then I will say that, okay, let us assume that P of k is true. P of k, so P of k writing is very simple. It just replace n with k everywhere. You really don't need to think about anything. So this becomes cosine x, cosine 2x, and this will be the next one, cosine 2 to the power of 2x. And then up to cosine 2 to the power of kx is equal sine 2 to the power of k plus 1 x divided by 2 to the power of k plus 1 sine x. Yes, so do you remember this is assumed to be true? And we want to show that this is also true for the next step. So I want to show that this is true for P of k plus. So I want to show that P of k plus 1 is also true, but before that I have to write it for k plus 1. So this means that I have to write this product, cosine x, cosine 2x, cosine 2 to the power of 2x, and this will continue until one step further. So this becomes cosine 2 to the power of k plus 1 x, and I hope that you have enough experience now that for these dots it's better always to write the previous step. So if I continue until I reach to k plus first step, it is natural that the previous step is the kth step, yes? So it means that it is better always to write the previous one as well. So this is the left-hand side for k plus 1. The right-hand side for k plus 1 means that replace k with k plus 1 everywhere. So this becomes sine 2 to the power of k plus 2x, and then divided by 2 to the power of k plus 2 sine x. So this is supposed to be proven, yes? Okay, so if you want to prove this, this is like an identity. Actually, this is an identity I want to prove. So it is better to start from one side if possible to use my assumption to reach to the other side. So I will start from the left-hand side, but the left-hand side up from here up to this point I don't have any problems with, yes? So actually the hard part is gone by the assumption. It's easy, yes? So I will say that if I want to show this, I will start again to write the left-hand side is equal to. So here, from here up to here, I know this is the formula based on assumed to be true part, yes? So I will take this away and put this expression instead. And then at the end, I will have this one as well. So this becomes equal to sine 2 to the power of k plus 1x divided by 2 to the power of k plus 1 sine x, but multiplied by cosine 2 to the power of k plus 1x. So this is what I get for the left-hand side. Okay, but now what can I see? So from here, let me use it a little bit differently. So let me just write here. So if I divide everything here by 2, I will get sine theta cosine theta is equal to 1/2 of this. So it means what? It means that if I have the product of sine and cosine of the same angle theta, I can write it 1/2 sine of the double angle, 2 theta, yes? And you see that in the numerator actually something like this is happening, yes? So sine, if you consider this in your head to be theta, that is exactly the same theta. Okay, so what happens? I am multiplying sine theta by cosine theta according to the same formula written slightly differently. I know that this combination is 1/2 sine of the double angle. So then this becomes equal to 1/2 sine of this angle multiplied by 2. And then in the denominator, I will have 2 to the power of k plus 1 sine x. And then this is just one simple step left, yes? So these 2 will go downstairs, and then these 2 multiplied by that will add 1 to the exponent, so it becomes 2 to the power of k plus 2 sine x. So you know that these 2 will go down, yes? And then these 2 multiplied by these 2 to the power of k plus 1 makes it 2 to the power of k plus 2, yes? And then I have x, and the whole thing is sine. And if you compare now this result with the result that I'm supposed to get, you see I am done. So that is equal to the right answer. Yes? Any questions here? questions? Okay, now there are, of course the lesson is again mathematical induction, but I want to show how you can prove sometimes inequalities related to natural numbers using mathematical induction. And I want to give you some examples that sometimes you can use this even in geometry. Yes, so there are some theorems or problems in geometry that are somehow related to the natural number n, and then you can solve that. So after that, the lesson is finished. Okay. So I think it's better to start with the example in the book. So here, example. Let n be a natural number such that n is greater than or equal to 4. Prove that two to the power of n is greater than or equal n squared. So this is the first time we want to use mathematical induction to prove an inequality. So far we always used it to prove equalities, yes. And there is a second difference here, is that this inequality turns out not to be true for smaller numbers than 4, yes. Might be, so I mean that if you want, you can set up a table for yourself here, n, and then 1, 2, 3, 4, 5, etc. And I can calculate 2 to the n, and I calculate n squared, yes. So if I put n equals to 1, this becomes 2, this becomes 1. Yeah, it is still greater than that one. That is correct even for n equals to 1. But the reason that they have started from 4, because there is no nice pattern going on. But after 4, it is guaranteed that this pattern continues. Yes. For example, if I go to 2, what happens? Again, that is not false. 4 greater than equals to 4 is a true statement. But for 3, it doesn't work, because this becomes 8. On the right-hand side, it becomes 9. So you see, only 2 was an exception. So they want to be on the safe side, and they want to show that this inequality is true for n greater than or equal to 4. Yeah, so it is guaranteed, if this is proven, then this is always true. So it means that here, for example, again, I get 16. Here I also get 16. But if I put 5, I get 32, and the other one becomes 25. And of course, these numbers now become much larger. Because, by the way, you remember, this is a polynomial, because its base is variable, its exponent is constant. But here it's an exponential. The base is a constant number, the exponent is variable. So exponential functions grow much faster, even though it might be they are dominated in the first few terms, but after a while, always exponential functions dominate polynomial functions. Yes, is that clear? Okay, so here that tells you that, okay, what is your statement? Your statement is this inequality. If you want to read it, this is also a statement. Statement tells you that if n is greater than or equal to 4 and a natural number, then 2 to the power of n is greater than or equal to n squared. So this means that the base of induction has changed from n equals to 1 to n equals to 4. So it means you shouldn't start with checking P1, because the problem is claiming after 4 and 4. So the first thing that you have to calculate is P4. You have to check the truth of this statement. Not for 1, for 4. Yes? So it becomes 2 to the power of 4 greater than or equal to 4 to the power of 2. This is, of course, equivalent to saying that this number is 16 is greater than or equal to 16, which is a true statement. Yes? So P of 4 is true here. But now, here I would say let K greater than or equal to 4 be a natural number. Such that P of K, which means 2 to the power of K greater than or equal to K squared, is true. So I'm assuming that K greater than or equal to 4 is a natural number. On top of that, I am assuming that this statement for that particular value of K is true. And then I want to show that the next step is also true, yes? So we show that P of K plus 1, what is P of K plus 1? I replace K with K plus 1. We show that this is also true. Yes? Okay, do you have it? So this is, you have to find a way. This is your assumption. You know that this number is greater than or equal to K squared if K is a natural number greater than 4. You want to convince yourself that if this is true, this one also is true. So what should I do? I don't know, might be there are different ways. For example, I prefer to start with the statement that I know it is true and try to do some algebra to be able to get something similar or exactly here. Yes? So let me tell you. So I start with 2 to the power of K is greater than or equal to K squared. Okay, I want to somehow start from here and prove that the second inequality is also true. So what can I do first? You don't need to see everything, but at least I see on the left-hand side of this, here, on the left-hand side, I have K to power plus 1, K plus 1, 2 to the power of K plus 1. But here I have 2 to the power of K. So what I'm supposed to do?
Add 1 to both sides.
Multiply. Yes, multiply 2 on the other side, so on every side. So 2 to the power of 2K is 2 times 2 to the K is greater than or equal to 2 times K squared. Okay, this becomes exactly what I need. So it becomes 2 to the power of K plus 1. But the right-hand side is not exactly what I need in that inequality. And that is usually the case. If you want to prove inequalities, don't expect that you can make both sides right. You usually can do one side right, and that is enough because you do not want to prove equalities, yes? You want to prove that this number is greater than or equal to that number, yes? So far, I didn't succeed to show that yet, but I succeeded to show that this number is greater than 2K squared. Okay, I would say that if I can show, so this is if, I can show that 2K squared itself is greater than or equal to K plus 1 squared, then I am done. This I want you to understand, yes? Do you agree with this statement? I wanted to show that K to the power of K plus 1 is greater than or equal to this one, K plus 1 squared. But I didn't succeed to show that. Instead, I succeeded to show that 2 to the power of K plus 1 is greater than or equal to K squared. Yes? Do you agree that if I can show that this also holds, then I am done, yes? Because I know that this is true based on the assumption. if I can show that this is also true, comparing this one and that one, I am done. Because this tells you that this number is greater than this number, and then this number itself is greater than that number. Comparing these two gives me the result. Yes, is that understandable? So that should be the logic when you want to prove inequalities. Don't think that you can always find it exactly right, yes? You are not supposed to prove equalities. You are supposed to prove inequalities. So this sentence you have to add, and then instead of, so it means that I will focus to be able to prove this one. And the proving this one is usually, might be hard, but not for these simple cases that you have in your book. So if I want to show that, this is very important, that you simplify this expression in an equivalent way, because this is not still trivial for me. If you ask me, is it always guaranteed that this number is greater than that number? I don't have a very good answer right now, but I can simplify it in an equivalent way. What do I mean? I mean that, let me explain to you. So I will write to a k squared greater than or equal to, this one squared becomes k squared 2k plus 1. So what does it mean? It means that if you tell me this, I can go and write this, or if you tell me this, I can go back and write this. So this arrow is double-sided. You can go back and forth. Yes, that is important. But is this clear for me right now? No. So what can I do, for example? I can move these two terms to the left in an equivalent way. So that is an equivalent way to do that. So 2k squared minus k squared is k squared, and 2k to the left is minus 2k. Is greater than or equal to 1. Is it still clear that this is true? Probably not that much. But then what can I do? I can add one unit to the other side, to both sides actually, so it becomes k squared. The motivation is to make a complete square. Is greater than or equal to 2. But that is also reversible. I can subtract 1 from both sides, yes? But this one is now what? Is k minus 1 squared is greater than or equal to 2. So what I'm telling you, I haven't proven anything so far. I have shown that this statement from mathematical point of view is equivalent to the last statement. Yes?
Why is the 2k to the power 2? How should that word be?
Pardon?
Should it be small than k
No.
plus 1 to the 2?
No. I want to show that 2 to the power of k plus 1 is greater than this number.
Yeah.
So my goal is to show that a is greater than or equal to c. I know so far that a is greater than or equal to b. So my question is that write something in this question mark so that I can conclude this.
B is equal to or smaller than.
No, why should I smaller?
I don't know.
This, no, because if you say a is less than or, no, b is smaller, so this is your guess, yes?
B is equal.
So you are saying that, let me write this, you mean, to be able to conclude that. So you see here, assume that here is b, and you know that a is somewhere after b, so here is a. Yes? If I have b less than c, it might be that c is here. Yes, you see here in this scenario, a is greater than or equal to b, do you agree? It's on the right hand side. And b is less than or equal to c because b is on the left hand side of c. Can I conclude that a is larger than c? You see, no, a is less than c. It might happen that in some cases you are right, but that is not guaranteed. Is that clear? Yeah. So that is why we have to do that. Okay, so here, what I have shown is that this is a question mark. Still, I don't know. What I did, I simplified this. I couldn't say I simplified that. I rewrote it in a way that I can know the truth of the inequality. So this is now guaranteed to be true. Do you agree with me? Because do you remember what was k? K, the minimum value for k was 4. Okay? So it means that if I ask you what is the minimum value of this expression, you would say 3 to the power of 2. That's the minimum value of k minus 1 squared. And the minimum value is already larger than 2. So other values also be larger. So you see, even though I couldn't immediately understand that this is always true, I simplified this to something that I can conclude it is true based on my assumption that k is greater than or equal to 4. Yes? Is that understandable? So the last statement is true, and this statement is equivalent to what I wanted to show. Because this statement is true, so this statement is also true. And when this statement is true, I am done. So you have to understand the logic. Yes? Is that clear? So you see, I wanted to show that this happens to be true. I started from my assumption that I assumed to be true and try to do some algebra to go from here to here as usual. I want to do the same algebra. But I started here. I see that I need 2 to the power of k plus 1 here. It motivated me to multiply both sides by 2. It's good partially. Why? Because on the left-hand side, I get exactly what I need. But unfortunately, on the right-hand side, I get something which is not this one, and it cannot be simplified to that one. 2k squared, it doesn't matter how much I simplify it, it will never be k plus 1 squared. So there is no hope that I simplify it and I reach to k squared. Is that right? So I have to change my strategy. The strategy here is this. I would say to myself, my goal was to show that this number is greater than that number. I didn't succeed to do that, but I succeeded to show that this number is greater than that number. Yes? So this is, you see, 2 to the power of, if I tell you, do you agree with this one? You should say yes. Why? Because I started from something which I assumed to be true, and I got this one. So if you say this is true, you have to admit this one is also true. But my goal is not this one. My goal is to show that 2 to the power of k plus 1 is greater than or equal to k plus 1 squared. This is what I was able to do. This is what I need to do. Okay? And there is no way that I can simplify this one to reach to this one. They are not equal. 2k squared is not equal to k plus 1 squared. It doesn't matter how should I simplify it. But then I have to change my strategy. If I can show that 2k squared itself is greater than or equal to k plus 1 squared, of course, here it's still not clear. This is clear, yes? If I can show this, then comparing these two, I can conclude what I need. Is that understandable for everyone? So this means that if I can show this part, then I don't have any problems to conclude this. Why? Because if A is greater than or equal to B, B itself is greater than or equal to C, we know that we can immediately conclude that A itself is greater than or equal to C. Yes? Okay, so this is the point. So I know that. I ask myself, can I prove this one? Why this is good? Because combining these two results, I get the result that I want to reach to. Yes? So then I started seeing that if this is true or false. But it is not that easy immediately convince myself that this is true. So here I start simplifying my inequality up to a point that that inequality is guaranteed to be true. Yes, but in an equivalent way. So that I can go back and forth. Going back and forth means that this statement and that statement they are different apparently, but mathematically they are equivalent. What is the meaning of statements being equivalent? Means that if one of them is true, the other one is true, and if one of them is false, the other one is false. That's the meaning of the being equivalent. So what I did, I squared this one as usual, and then I move this k squared to the left. It becomes k squared. Okay, for example, of course you can do some scratch work, so you say that k squared is greater than or equal to 2k plus 1. So it's still not clear, you know, why k squared should be greater than 2k plus 1. It is not that clear. So I decided to continue. So I moved 2k to the left is greater than or equal to 1. It's not, for example, if it was positive, then I don't need to continue. Why? Because k is a number greater than or equal to 4, and this one and that one are positive and greater than 4, definitely it is greater than 1, I stop there. But here, no. Because one of them is increasing, the other one, because of this negative sign, is decreasing, so I have to convince myself which one will dominate, yes? So this is why this is not a good stopping point. I continue. How? I decided to add one unit to both sides, and then this becomes k minus 1 squared, this becomes 2. But now, is this guaranteed? I would say yes, because I know that the minimum value for k is 4, then definitely the minimum value of this expression is 9. And if the minimum is 9 and it is already greater than 2, let alone other values, so all of them will be greater than 2. So this means that now it is guaranteed that this is true. This means that this is also true. This means that that question mark is now checked. Then I can conclude what I need. Yes? So this is what you need to expect when you want to prove inequalities. Yes? Of course, they have done it a little bit differently in the book. You can also see that this is a solved example in the book. There's only one example solved in the book, so let me give you a little bit more examples. Okay, so let me write this example. Let x be a real number let me write a positive real number. Let x be a positive real number show that for all natural numbers n, we have this inequality. 1 plus x to the power of n is greater than or equal to 1 plus n times x. Okay, I will repeat everything more or less. Again, don't get confused. You see, I have two variables involved in this problem. One of them is x, is a real number, so you cannot use induction on x. You can use induction only on natural numbers. So I have to use induction on n here, not x. Okay, so this is your statement now. So the first thing that I have to do here, by the way, it is for all natural numbers again. So it means that my base of induction starts with 1. So I check this inequality when n is equal to 1. This gives me 1 plus x to power 1 greater than or equal to 1 plus 1 times x. So this is the P of 1 statement. So is it true or false? Actually, this is true because both of them are equal in this case. So this is equivalent. 1 plus x to power 1 is nothing except 1 plus x. 1 plus 1 times x is nothing except 1 plus x again. And this is claiming that 1 plus x is greater than or equal to 1 plus x. But this is a true statement, yes? So we check that P of 1 is true. Now I would assume that, so I don't need to write an extra sentence here. Here you see I wrote let k be greater than or equal to 4, but this is for all natural numbers, so I really don't need to emphasize on that. K is an arbitrary natural number, k. So I would write this statement for k, so it becomes 1 plus k to the power, 1 plus x to the power of k is greater than or equal to 1 plus kx, assumed to be true, yes? Okay, but I want to prove it for the next step, pk plus 1. So what is that next step? It becomes 1 plus x to the power of k plus 1 is greater than or equal to 1 plus, I replace k with k plus 1 everywhere, yes? To be proven, yes. Yeah, we have a little bit of space here, so let me just do it. But I want to ask your opinion about that to make sure that you're understanding. So you see, I know that for every positive x, by the way, this is not, okay, so I made a mistake. This is not working for positive numbers. So let me write it like this, sorry, because I realized that this is not enough. So I would say let x greater than minus 1, this is crucial. Positive will not work. Be a real number. Yeah, sorry. Okay, because now you will see why this is needed. Okay, can you help me now? This, I assume that this is true. I'm assuming that for any number, real number greater than minus 1 like x, and for any natural number k, I assume that this inequality is true. I want to show that based on this, definitely this inequality is also true. So what should I do you think here? So you need to think in this way. How can I somehow do some algebra that takes me from here as close as possible to here? Because now you have experience. For inequalities, it might not be possible to get the exact inequality. So it means that you want to make yourself as close as possible to what you're supposed to prove. So can you tell me what to do? For example, I start from here, which I know it is true. Okay, now can you tell me what to do? You don't have to see everything, but something is actually highlighting what to do, at least for it might not be true, but we have to check it out, yes? If it is working, it's working. If it's not working, we have to come back and correct it. But what can I do? Do you think I want to go from here to something close to the one that I want to show? Any ideas? The idea is exactly as before, because you answered me multiplied by 2, and I did it and it worked. So there should be a similar idea here as well. What should I multiply everything by?
1 plus x.
1 plus x, yes. Because you see that here, if I ask you what is the exponent, you'll say me k, but in what I'm supposed to show, what is the exponent is 1 unit more. Okay, that is enough for a starting point. I'm not saying that this is probably 100% it will work, but we have to try it. And that's a very good point to start, yes? So I multiply everything by 1 plus x. And now you see that this is indeed necessary. What I wrote in the beginning was not that correct. Because if I multiply both sides of an inequality by a number, if that number is positive, then I am entitled to keep the sign the same. But if I know it is negative, I have to flip the sign. Do you remember? And now, what is guaranteeing that? Don't worry about that assumption. Because when you say x is greater than 1, it automatically means x plus 1 is positive. Yes? And now that 1 plus x, sorry, if 1 plus x is positive, I can multiply, and I don't need to be worried about flipping the sign or whatever, because 1 plus x, according to the assumption it given in the problem, is positive. So it means that I just multiply. So I multiply. It becomes this. Here, at least, oh sorry, this is k. This is exactly this one now. It becomes 1 plus x to the power of k plus 1. On the right hand side, let me multiply that. So what happens? It becomes 1 times 1, 1 times kx, x times 1, x times kx. Yes? So if because my goal is to make this as similar to this. Yes? So what can I write? I can write 1 plus x to power k plus 1. I have 1 here, and I also have 1 here, so that is a good sign. So let us keep it. But here I have kx plus x, and you immediately realize that you can factor an x out, so it becomes k plus 1 x, and that is also excellent, because I have it here. But unfortunately, I have an extra term, apparently, and there is no way for me to get rid of that extra term. Is that understandable? So I was able to simplify that, but I was not able to get rid of that term. So this is my advice. Don't think that when you are proving inequalities, this is very common. You are usually not able to get exactly what you need. So don't think that you have made a mistake. What you need to ask yourself, you should say that, okay, I want to prove this. I was not able to prove this, but I was able to prove that this one is greater than this one. Then you need to write a sentence for me. What should I write? I would say that if I can show that, okay, I want you to fill up the blank, then I am done. So can you tell me what should I write in the blank here? If I can show what, then I am done. Yes? Yeah, Kevin. Yes.
If 1 plus, that term.
Yeah, just read it, don't be lazy.
Okay,
Yes.
1 plus k plus 1 x plus kx squared is equal to or larger than 1 plus k plus 1 x.
Yes. Do you agree? My goal is to show this one. I didn't succeed to do that, but I succeeded to show that what I need is greater than this combination. If it is possible to show that this itself is greater than this one, then comparing this one, which is true based on my assumption, and this one, which I am able to show if possible, then I can immediately conclude what I need. Yes? But in this case, it is even simpler than the previous one. Do you agree that this one is greater than this one always? Because this one is the same one. This combination is the same combination. You are adding something to the left, and it is guaranteed that this is positive. Why? Because x might be x is negative, but x squared cannot be negative. And then k is a natural number. So this combination is definitely a positive or at least 0. So this means that the left-hand side is guaranteed to be y. You can say that this itself is equivalent. Simplify everything. Okay, so this inequality is completely equivalent to this inequality. But is this inequality guaranteed to be true? The answer is yes, because x squared is non-negative, even if x is negative. And k is a natural number, so it means that the multiplication is definitely non-negative. This is true. This is definitely true. This is equivalent to what I need, so it means that what I need is also true, and then this one and that one I have. Yes? Is the logic clear? Okay, so that is the logic that you have to have in your mind when you are dealing with inequalities. You shouldn't expect to get exact algebraic expression that you need. Okay, and now let me just go to the next example that sometimes you can use it in geometry. This is a good example, so let me start with an example here. So let me write it here on the board. So first of all, if I have a polygon, it means that I have a shape with some sides, a straight line segments. But then I can have two types of polygons, convex or concave. We are not dealing with concave ones. What is the meaning? For example, here, if I draw this quadrilateral, let us confine ourselves for 4 sides. This is called a convex quadrilateral. What does it mean? It means that if you continue each side, it doesn't matter which side, then the whole polygon lies on one side. Yes? So if you see, if I draw that one, the whole polygon lies here. And if I draw that line, the whole polygon lies on the left-hand side here, for example. If I draw this one, then the whole polygon is up. And if I draw that one, the whole polygon is on the right. Yes. So that is the meaning of having a convex polygon. But I can also have something like this. Let me make it better because I need one more. So that is also a quadrilateral. One side, 2, 3, and 4. But this is not convex, it is concave. Why? For example, if I continue this side, then you see one part of the polygon is on this side and one part is on the other side. So this problem that I want to talk is about the convex polygons, not only quadrilaterals, yes? So, this example show that the number of diagonals of an n-gon let me write it, a convex n-gon. So n-gon means a polygon with n sides. So that is common. They call it n-gon. So show that the number of diagonals of a convex n-gon is n times n minus 3 divided by 2. So you see that's a problem in geometry. So you have a shape, a convex n-gon. It means that you have a shape with n straight sides and convex in this sense. And you want to show that the number of diagonals of such an n-gon is n times n minus 3 divided by 2. So how should I do that? First of all, can you tell me where is the starting point of my induction? What is the base of induction for this sentence to make sense? If I want to write, let me write Pn. What is Pn? Pn, the number of diagonals, let me make it short, of an n-gon, of course a convex n-gon, is n times n minus 3 divided by 2. So this is my claim. That is my statement. You see, this statement is a statement regarding the natural number. It doesn't matter if it is in geometry, but this claim is a claim about a natural number n. That is important. Okay, I want to prove that. So do you think I can start with checking P of 1? Because 1 gon, we don't have it. So the smallest n-gon that we have is 3 gon, and that is a triangle, yes? So it means that if I want to check the statement, you know that if I have a triangle is a 3 gon because I have 3 sides. So this means that I have to check it for 3. You need to write the statement. The number of diagonals of an 3 gon has a better name, triangle, is how much according to the claim? 3 times 3 minus 3 divided by 2. But if you calculate this number, is 0. True or false? It's true. Because in triangle, we do not have any diagonals at all. Yes? It's a true statement. Okay. Now, I would say let k greater than or equal to 3 be a natural number. Such that P of k is true. What is the meaning of P of k is true? It means that the number of diagonals of a k-gon is k times k minus 3 divided by 2. Namely, let me write this, namely, let the number of diagonals of a k-gon be k times k minus 3 divided by 2. Yes? Now what I'm supposed to show, I'm supposed to show that P of k plus 1 is also true. So it means that if I have a polygon with k plus 1 sides, the number of diagonals follow the same formula, but for k plus 1 instead of k. So we show that P of k plus 1 is also true. That is, we show that the number of diagonals of a k plus 1 gon is equal to what? I have to change k to k plus 1 everywhere. So this becomes k plus 1, but k plus 1 minus 3 is k minus 2 divided by 2. Yes? Yeah, is that understandable? So if I can show this, then I am done. So let me repeat this, because here, in principle, if you really want to write it right, you have to write a lot of words, English words, yes? So I am assuming that I want to show this. So this is my statement that I want to show. And I checked it for 3, which is the smallest polygon that you can imagine. And then it means that the number of diagonals for such a shape is 0, and it is correct. There are no diagonals for a triangle. Now I assume that k is a natural number greater than or equal to 3, and I assume that the statement is true if I have a k-gon. What does it mean? It means that if you give me a shape with k sides, I agree, I admit that the number of diagonals is this number. Now, what I have to show that if you give me a k plus 1 gon, the formula remains the same. What does it mean? It means that if I go to my formula, replace k with k plus 1, that is also true for k plus 1 gon. Okay, so how should I prove that? So you need to have an idea how you can go and count the number of diagonals for a k plus 1 gon using this information that you already know the number of diagonals if you have a k gon. Yes? So this you need to connect the idea. How can I use this piece of information about the number of diagonals for a k gon and use it to count the number of diagonals for a polygon with 1 vertex extra? Yes? So how can I do that? So for example, let me take this one, vertex number 1, vertex number 2, vertex number 3, and then I continue, vertex number k, and finally vertex number k plus 1. Yes? So you can imagine that I have k plus 1 vertices for the k plus gon, and I want to count the diagonals here. So how should I do that? But of course, one way is to draw all possible diagonals here and try to count them, but it is not very efficient. I want to somehow use my information regarding the k gon. So how should I do that? Any ideas? So let me make it a little bit clear for you. So, for example, how many diagonals are there for a square? 2, yes? And now I want to add 1 vertex here. So if I give you, I have 5 vertices. So this pentagon can be viewed as this quadrilateral with 1 vertex extra. Yes? So if I count a diagonal here, this is a diagonal for my quadrilateral. But do you think that this is also a diagonal for this pentagon? Yes. So it means that any diagonal that I count here is playing the role of a 1 diagonal for even bigger shape. Yes? Is that clear? So that should be somehow the idea. So what I can do, I can connect this one to that one, and then this one to this one, and etc. So you see, if I ask you what is this, you would say that this part of the shape is a k-gon. Yes? And then I have 1 vertex extra. And if I ask you, do you know how many diagonals are here? You would say yes. The number of diagonals there is this number. And every diagonal that I count here for the bigger shape is also a diagonal. Is that understandable? Okay. So the number of diagonals for the k plus 1 gon here is equal to the number of diagonals in a k gon. which I know by assumption, is k minus 3 divided by 2. But these are not the only ones, do you agree? The bigger shape has more diagonals. For example, here, this one was a diagonal for a pentagon, but for this pentagon has this diagonal, yes? This was a diagonal which was not considered in the previous shape. So there are some new ones that I have to add to this number. So all of these diagonals are still diagonals for the bigger shape, but the bigger shape has more diagonals. So how many more? If you can count that, then you are done. How many more? It's not hard. You see how many more I can count. So, for example, here, if I connect this one to this one, do you think it's a diagonal for the bigger one? This one is not a diagonal, it's a side. Yes? This one is not a diagonal, it's a side. But any other ones, so if I connect this one to this, and to this, and to this, and to this, here, and to this. So if I ask you, so let me put some dots here. So if I ask you how many orange lines you see at the end, how many orange lines you see? If I connect a sub k plus 1 to every other vertices, how many orange lines you will see? How many orange lines? How many vertices are here? From number 1, number 2, number 3 up to number k. So how many vertices you see here? K. And then how many orange lines you will see? K. Yes? But 2 of them are sides. So I have to exclude them. Yes? So if I ask you how many orange lines you see here, because there are k vertices left for me, and I am connecting this point to all of them, so there are k orange lines that you see, but 2 of them will not play the role of the diagonal. They are sides, so I have to subtract 2 from it. Yes? I hope that you agree what I have written is the number of diagonals for the bigger shape. Is that understandable or not? Yes or no?
Yes.
Okay. So then we have to simplify this and confirm that this number is exactly equal to that number, if I can do that. And then the algebra is probably very simple. So what I do, I take the common denominator 2. This I multiply in, it becomes k squared minus 3k. But then I have to multiply 2 here, which becomes positive 2k minus 4. And then what happens? This becomes k squared minus k minus 4 divided by 2. And hopefully you agree that this is exactly, no, you shouldn't agree, this is not exactly the same number. Oh, I made a mistake. What was my mistake? This is not working, you see? So there is a mistake that I have done. Can you say what?
Oh.
What is that mistake? Yes?
Did you count the diagonal to itself? Like the point to itself?
No, to the point itself, no. I didn't count. But that is clear what I have done. Yes? But I have to add 1 to it. Can you tell me why? So if I ask you what is this number, you will tell me this number is the number of diagonals of this shape, which is a k-gon. If I ask you what is k minus 2, you will tell me that k is the number of orange lines, but 2 of them are sides, and I will not count them as diagonals. So I subtract 2 from it. But now my question is that, I made a mistake, sorry. I have to add 1 to it. Why?
Because the side A1, AK was a side before.
Now it is a diagonal. Do you understand? This side, I didn't count it here because I counted only the diagonals here. A1, AK is not a diagonal here, it's a side which is not counted here, but now for the bigger shape this plays a role of a diagonal. This means that I have to add 1 to it. Is that understandable? Now that was my mistake, sorry. So now I have to continue. So what happens here now? This becomes k minus 3 divided by 2, and then k minus 2 plus 1 is k minus 1. And now I follow the same method. I take the common denominator to be 2, I multiply this here, so it becomes k squared minus 3k, and then k multiplied by 2, 1 multiplied by 2. So if I simplify that, this becomes k squared minus k minus 2 divided by 2. And that is exactly this expression. You see, this becomes k plus 1, k minus 2, and then divided by 2. So if you don't agree, you can multiply. K times k is k squared, k times minus 2 is minus 2k, 1 times k is positive k, so it becomes negative k, and 1 times minus 2 is that one. So I was able to show this one. So that's also one application of a mathematical induction in a geometry problem. Yes? So you see that in all these problems, the important thing is that you have a statement regarding a natural number. So it doesn't matter if that statement is trigonometry, as in the first example today, or it is in geometry, or it is in algebra, or any other disciplines of mathematics that you would get familiar with it later. So even if you remember, the first starting example was the application of that in number theory for divisibility. So whenever you have a statement regarding a natural number, very powerful method to think about is, I'm not saying this is the efficient way, the most efficient way, but at least one way to think about how to prove that statement. Any questions? Okay, so I stop the lesson here, and then we will have the exam for next Monday, yes? And then I will not teach anything on Thursday. Thank you.